Going to be a little bit hard to read up there. I wanted to get the whole thing up on screen. So you got it in front of you too. It says, the rate at which a rumor spreads through a high school of 2,000 students can be modeled by the differential equation dp dt equals 6p minus 0.003p squared, where p is the number of students who have heard the rumor t hours after 9 a.m. So guys, first thing I want to point out to you, and you maybe already noticed this, did you guys notice that this differential equation that's mentioned in here as being a logistic differential equation? I guess you know what? It doesn't say it's logistic, but it is. Does that not look sort of different from the logistic that I showed you, like the last couple I showed you? So my first thought is, before we get into answering any of these questions, can you figure out how you could take that form and turn it into the form that you've already seen? Any suggestions?
Take out the P.
Take out the P. And what else? Go back and look at it if you need to. Go back and look at that other form of the diff-EQ that I showed you. I agree with the whole factor out the P idea. What else?
Divided by 6.
Well, let's, instead of dividing by 6,
Multiply.
factor out the 6. Yeah, let's factor out a P and a 6. Okay, so, Cole, can I ask you, you had the good idea of factoring out the 6. Why would I factor out the 6? And it's got to be that, doesn't it? It's got to be inside, it's got to be 1 minus something. And the only way you can get that is if you factor out the whole 6p. So it gives you 1, minus, golly. So factoring, when you factor something out, you're actually dividing it out. So what's 0.003 divided by 6? So 5 times 10 to the negative 4th. Yeah? 0.3 zeros and a 5. Okay. So 0.0005p. Is that exactly like the form we've seen before?
Yes. Well, almost.
Kinda. Doesn't that 1 minus, the second thing doesn't need to be a fraction?
Yeah.
So what it's p over what? I don't think so. 0.03 zeros and a 5? Or is it 2 zeros and a 5?
It's 3 zeros and a 5.
Okay, so 3 zeros and a 5. Do you know how to do this on a calculator? Get your calculators. Let me show you how to do this super easy. I have a faster way. And so either way you still got to do 0.005, right? You still got to type in 0.005. So guys, do this. Hey, type in these numbers exactly. 0.005. Isn't it? You said it was 3.
Yeah, but you said 2.
Or 3 zeros. Yeah, whatever that number is, 0.3 zeros and a 5. So type that in, and then right above on the left side by the log where it says log, and then go up 1 to where it says x squared, and then you see above that it says x to the negative 1. Just type the x to the negative 1 button and hit enter. So it'll flip it for you, right? It just flips it, and it's 2,000, right? 2,000. So that's a way you can just get the reciprocal of a number really quick. It's not going to convert something to a fraction, but it will reciprocate it. So, okay, so you get dp dt equals 6p times 1 minus p over 2,000. Does that make sense based on the way the question was worded? What's the one data point that says, hey, yeah, this could be accurate? The 2,000. The 2,000 is what? Carrying capacity, and the 2,000's in the right spot, right? Okay, so we at least have to look at this and say, well, at least for a school of 2,000 people, this seems to make sense. Why would the carrying capacity be 2,000?
That's how many kids are in the school.
Yeah, you can't have like 2,005 have heard the rumor.
Yes.
I don't think so. Unless 5 people are born in between. You know, who knows? People are getting cloned, right? Maybe it's in science lab, whatever. Okay. So, oh gosh. A says, how many students have heard the rumor when the rumor is spreading fastest? In other words, when is it just like blowing up and the rate is at its highest, right? The rate of hearing the rumor is at its highest. So, do you guys, shoot. Any ideas? Let me just, oh, did you hear that? He's got a pretty good memory. Say it again.
Well, you said like at the rate where it's increasing the fastest, that's always an inflection point. So you can just
Remember that graph I drew yesterday? That's what he's connecting. That's good. Okay. So this says how many students. So which letter would go with how many students?
P.
P. It's population, right? So let's just rephrase the question a little bit. What do you guys think the population would be when the rumor is spreading fastest?
Probably like 1,000.
I've heard probably like 2,000. I've heard probably like 1,000. I heard a reinforcement for one. Why'd you pick 1,000?
Because the inflection point was halfway in between the graph that we had yesterday.
Oh, okay. So you're just thinking about like relationship on the graph seemed to be in the middle.
Well, and it wouldn't be 2,000 because then like with the sickness there wouldn't be as many people to get sick. So like there wouldn't be as many people who hadn't heard who like the rumor could be spreading to.
Okay. So you're just referring to like scale. Like in our little world there was 20 people
Yeah.
and now there's 2,000.
Or so like if say like 1,900 people know the rumor, then only 100 people can find out. Versus if 1,000 people know the rumor,
There's a
then
lot more to be finding it out.
1,000 can be finding out. So there's a lot more potential, but there's also people who can tell them about it.
Sure. Okay. Sounds reasonable.
Thanks.
Very reasonable. Yeah. So the answer is both Jack and Liz have kind of hit the right mark. It's when you're halfway to the carrying capacity. Did you hear that? Guys, this is the easy button. There's a way to do this that takes a long time. So if you forget what I'm telling you right now, you're going to be forced to do this long process of finding an inflection point. Remember what that logistic solution curve looked like? You'd have to differentiate that to get back to this differential equation. You have to differentiate that again. You have to set that second derivative equal to 0. We're not talking about things that are impossible. We're just talking about things that would take a lot longer than saying, oh, rumor is spreading the fastest when you're halfway to the carrying capacity. So how many students have heard the rumor when it's spreading the fastest? P equals 1,000. So if you know that principle, we can prove it by finding the inflection point and finding the second derivative there. We already have the first derivative. It's not like it would take us an hour. It would take us like 3 or 4 minutes, but I'd rather it take you 3 seconds than 3 or 4 minutes. Josh.
Is DP the rate of students?
DP is the rate of change of students with respect to time, dp/dt.
Okay. So could we set DP over DT equal to 0?
What would that give us?
I got 0 in 2,000, which I know doesn't make sense. When you take the derivative of DP over DT and set that equal to
That actually makes perfect sense.
Yeah, but why would we find the rate of change of students?
Because that would allow you to find when P is steepest, which would be when the rumor is spreading the fastest.
So DP dt is the rumor graph, and then
DP, well, I don't know what you mean by the rumor graph.
like how many kids know the rumor.
No, P is the how many kids know the rumor.
So we need to find the rate of the rumor spreading.
Yeah, you need to find the rate of change of the rate that the rumor is spreading,
I see.
which is a second derivative of population.
I was confused in what we were finding.
Yeah.
Makes sense.
Does that make sense? Was there another question? Jaden or Jack maybe back there? No? Thought I saw a hand. Call?
So you're saying it's always the halfway?
When you are halfway to the carrying capacity is when the rumor or the sickness or whatever it is spreading the fastest. Yeah.
Is it from like at the halfway point that is, but it's increasing the most?
When
from
you are
0
when you
to
are at the halfway number to the carrying capacity, because you could get all kinds of shiftings, right?
Yeah.
Because it depends on how many people knew the rumor when T was 0. Right? You could think, oh, does it matter? You're still going to be steepest whenever you're halfway to the carrying capacity.
Yeah.
More or less for the principle that Liz said.
Yeah. So is it always going to be like concave up from like 0 to the half, and then like concave
Yep.
down?
Beyond that?
Yeah.
Yep, that's true.
Okay.
That's true. These are great questions. So I think that it might bring up more questions, but it also might answer some of these questions if we did B. You guys okay with B? It says, for B, it says if P of 0 equals 5, solve for P as a function of T. In other words, you're supposed to come up with the solution curve based on the differential equation. What's the mnemonic device to help us with this? Mice minus Katie. That's your solution curve, okay? I don't know too many times when Katy Perry is the solution. This is the time when mice minus Katie. That's the solution curve, right? Okay. Probably depends on the question, right? Okay. So, guys, take a minute. See if you can use that mice minus Katie mnemonic to, excuse me. Thank you. To come up with this solution curve for the population that has heard the rumor. And once you think you got it, you can see the next thing is going to be, we're going to graph it on the calculator.
Another song from
I heard it was the hair brush. No.
M is your carrying capacity. So in this case, the carrying capacity is 2,000.
That's pretty neat.
M should be.
I don't know. It never gets
Please be the water
never gets to
buffalo.
that much score. And it's not Pirates of the
He's always talking and then he just interrupts himself with the paper.
Oh, Jack just found it. He's wondering if you can find it, right?
Even if he doesn't know.
DPDT equals KP times 1 minus P. Once you know the phase, use that as a boundary condition.
We use 0.5%.
You guys doing okay finding the K? I'm not talking about the C, I'm talking about the K. Right, because it's M over 1 plus CE to the negative KT. So we need a C and we need a K. The K is actually right in front of you. Might be hard to see still.
How did you know? He said it's right in front of me.
What do you think the K is? You say it.
He just said, Alex, are you the K? He's right.
Not this time. Not this time. Any ideas?
Let's see.
It's on your paper. You got it?
It's... Why is it 6? The K's the constant. What's the K?
Oh, what's M? Oh, max.
What's her
If you're having a hard time finding the K value, I've written it up there for you. In order to have this solution curve, you got to have the K and the C.
Why didn't it take like 10 minutes to see the P of 0? That's so annoying. Should be the graph. What? Did you just say gosh, Jake?
Yeah, it's got the sand stuck in it. Yeah, me too.
So it says if P of 0 equals 5, solve for P as a function of T. Well, there's a couple things we can do right away. I know for sure that P is equal to 1,000 over, not 1,000, excuse me, 2,000 over 1 plus CE to the negative KT. I can start right there, right? Because I know my carrying capacity is 2,000. That's the M in the numerator. I don't know the C and I don't know the K. The K actually, like I said, is right up there, right? If you can look in your differential equation and see where the K is, it's a pretty easy plug-in. K is 6, right? And I'm getting that simply from there, right? K is 6. It's one of those things that's like so obvious that it's not obvious. It's hard to see. It's there. So then we could say that P is equal to 2,000 over 1 plus CE to the negative 6T. So then what's my final step? How am I supposed to find the C?
Solve.
Using Yeah, 0 and 5. Yeah, P of 0 equals 5. I can then say 5 equals 2,000 over 1 plus C e to the 0. Cross multiply. Jeff got 399. I think he's right? Okay, so C equals 399. So therefore, my solution curve with everything in there, 2,000 over 1 plus 399 e to the negative 6t. Say again? P of t? You want me to write P of t? Okay. P of t. Okay. So then, did you guys take a minute and graph this? Those of you that maybe got to the end. If you haven't, please do. Please do. I want to just kind of connect back to a few features that we looked at yesterday. Don't I know that? Don't I know that P of 0 equals 5? Know that that point's on my graph.
Keep doing that. Too much.
You need to get your window fixed there? You don't feel like fixing your window?
It's right at the top.
Oh, interesting. Did you go up to 2,000 on your window?
Yeah.
Okay, yeah. There you go. Oh, and there's your midpoint. So did you already move on to C?
Yeah, indeed.
That's a good idea. All right, did you guys get something like this?
It's a little steeper.
Yeah, I spread my x-axis out a little bit. Your guys is
What's
right.
your window? We got a
Yeah.
kind of window.
My window is big enough for it to look like that.
Oh, okay. Okay.
Whatever that
It's
is.
small enough that that's wrong.
Something like that. What's that?
The person is only 0.1 away of a person.
Oh, well, so
I was wondering.
they heard the rumor, they just didn't understand it. Right? They're just kind of like, what?
I think it looks more like a horizontal line.
Isn't it interesting the lies your calculator can tell you? You're like, no, it doesn't look like that at all. It's something totally different.
I made the window like 100,000 for a lot.
Okay, is this okay now?
Yeah, she forgot her. So you forgot like graph? I don't remember.
I'm literally like in my y equals, I'm putting in 2,000 divided by parentheses. Make sure you put parentheses on your denominator. 1 plus 399 e to the negative 6t. So your window on your y's, I'd go like 0 to about 2,000. And on your x's, I don't know, 0 to, I don't know. That shouldn't matter.
0 to 2.5.
Yeah, my calculator just like there.
2.5? 2.5 works? Okay.
I get this.
I put it in, I just listened to what they were doing. I put it into my calculator.
See, mine just doesn't graph it. Mine just is 2,000 for everything. Oh, that's why. Mine just doesn't have y values.
Okay, so your window is probably the issue. So I'm going to go like 0 to maybe that, but then I'm going to go 0 to 2,000.
I don't know how to. Do you know how to add y
Yeah,
values?
you're just, you weren't seeing hardly any of it.
Wait,
Your window has to be like window has to be 0 to 6, like y max
Mr.
is
Anderson, can you help me?
You have it put in there okay?
Yeah, but nothing's showing up.
Yeah.
Let's look at your, yeah, that looks, oh, this is the wrong E, my friend. Let's go, you're using the times 10 to that.
Yeah,
So
yeah.
E2 though. Negative 6x.
Wait, is this how you're ready?
I've been in chemistry too long.
There we go.
Oh, that might work me out.
So maybe go window, maybe the X max should just be like 10 or
So now we're trying
something.
to find one Y.
There we go. Hey guys, got a couple of really good things here for you. Hey, again, in the interest of helping you knowing all the things you might be asked, I want to ask you guys a couple of questions. So I think are we all okay with the graph now? Okay, so what if I said this? What is the limit as t approaches infinity of p of t? Limit as t approaches infinity of p of t would be 2,000. Because as t continues on and on and on, shouldn't we be approaching the carrying capacity? Okay, let me ask you a slightly different question. What is the limit as t approaches infinity of dp dt?
0.
0 is right. Why?
Because it won't be changing anymore.
Because we're doing what?
The students can't be negative.
Students can be negative, I agree, but as t goes towards infinity, the number of students is approaching 2,000, like you said before.
We're maxed out.
Therefore, the rate of change would be 0, right? Because you're getting closer to that carrying capacity. I hope you guys are paying attention. I'm throwing down some really quality shortcuts here for you. Choose to take them or don't. I'll let you sink or swim. Okay, any questions? Okay, so then C says use your answer from B to determine how many hours have passed when the rumor is spreading the fastest. That connects with A a little bit too. And then D says use your answer to B to determine the number of people who've heard the rumor after 2 hours. So let's see if we can do C and D. It kind of connects back to everything we've been doing. You can do this in large part on the calculator. See how it goes. C and D. Give you a couple minutes to do this one.
That's so much.
So for C, it says use your answer from B to determine how many hours have passed when the rumor is spreading the fastest. Well, we already know that it's 1,000 people, right? So what I would do here is I would say 1,000 people equals 2,000 over 1 plus 399 e to the negative 6t. I'm simply going to say, I know the number of people. Now all I got to do is find the time. I'm going to multiply across and divide and do all that stuff. I'm hoping you guys came up with a solution to this. T equals what?
0.8826.
You guys agree with that? 0.883 approximately? 998? 998. That sounds like that's the majority of people who came up with 0.998. I guess I'll trust that.
Oh my gosh.
Yes, you'd end up with you'd end up with 399 e to the negative 6t equals 1. Divide by 399, ln, divide by negative 6, right? You guys good? You guys happy with that? Okay. And then use your answer from B to determine the number of people who've heard the rumor after 2 hours. So that would be P is equal to 2,000 over 1 plus 399 e to the negative 6 times 2, or e to the negative 12th. Again, obviously a calculator exercise. Nick seemed to indicate that there was like a fraction of a person that heard the rumor. What was the number you came up with?
They heard it, they just didn't believe it.
So it's just... Say the whole thing again?
1,995.109.
109. So it's that 109.109 that my joke with Nick was they heard it, but they didn't get it. Yeah. Thanks for the courtesy laugh, Colin. Well done. Okay. Guys, any questions at all? We're going to leave logistic alone for now if you don't have any questions. Okay. So we're going to revisit something. Hey, listen. Hush. We're going to revisit something. I got to push pause. Outside the box topic of the year, I think. This is the final outside the box topic of the year. This is differential equations that are, at least at first, not separable and would normally be something we wouldn't know how to do. These are called first-order linear differential equations. And I showed you how to do one of these the other day when we were doing those slope fields. And we're going to revisit these. And maybe we'll just do one of them today. And we'll do another one some other time. Let's fix it in as a review question. Yes, sir.
So when you say outside the box, do you mean like one of the ones that's not on the AP?
So, yeah, this is not on the AP framework. It's not anything I would test you on a final or next semester. The only time I would assess you on this is for this particular unit of material. Okay, so, just a couple of quick things here. I got to tell you, I'm not a fan of the formula. I'm a fan of, seeing the pattern. But I do want you guys to understand that a first-order linear differential equation is specifically this. The dy dx is simply just that. There's nothing being multiplied by it other than a 1, technically. It's simply dy dx plus some function times y equals some function in terms of x, or perhaps a constant, who knows. So this is what's called a first-order linear differential equation. And so this is the form we're going to talk about. The way to be able to handle this is you got to form this integrating factor. And the way that you form the integrating factor is this. Integrating factor is e to the integral of p of x, where p of x is this. Okay? And then we're going to use that to help us get to a better place where we can actually solve the differential equation. Remember, a differential equation, like the solution to a diffie-q, is very simple. It's simply the equation that if you differentiated it, you'd get the thing you started with, right? So the answer is an equation. Sometimes, a lot of times, the way that you get there is challenging. So let's just do the one example that's coming up here. There's two of them. Let's just do the first one. So here it is. Example number 1. It says, find the general solution to that. Excuse me. So let's just take a second here and recognize that this is one of those first-order linear differential equations in the sense that it's dy dx plus 2xy equals 10x. That fits that framework from before. If you ever do take a differential equations class, you'll find that a lot of it is based on form. Like, can you look at this and see, oh, it's like that one, therefore I will do this. Oh, wait, no, it's like that one, therefore I've got this different procedure. It's like selecting from a menu of frameworks. You match it up and you're like, there's my procedure. Or you match it up with this other one and it's a different procedure. This is just an example of that. So let's see if you guys can find this integrating factor first. The integrating factor is the thing that will allow us to see a pattern that will lead us right directly to our solution. Give you a second to do that.
So when you're doing the integrating factor, do you still include the plus c, or will it eventually just cancel out?
So this is a general solution, and so obviously at the end there will be a plus c. But as you're doing the integrating factor, we're not going to include the plus c because it's not really like the antiderivative of the whole thing.
Okay.
We're just saying, okay, we need to get this expression to allow us to find the antiderivative. Whereas when we find the general solution, that'll have a plus c on it. So we're just using like the integral as like a tool to enable us to see a pattern, not as a finished product.
All right.
Yeah. You could break into song, right, about this, as we heard today. All right. So guys, your integrating factor would look like this. U equals, it's usually a letter U for whatever reason, e to the integral of 2x dx. You guys come up with that? Okay, so of course the antiderivative of 2x is x squared, so our integrating factor is e to the x squared. So I don't know, maybe you read a little bit on that front page, or maybe you remember from last time. Does anybody remember what we do with that integrating factor?
Multiply every term.
Yep, it's called, think about the word, it's called a factor. And doesn't factor bring up to mind multiplication? So we're going to multiply every single term through by that integrating factor.
So people just like figure out how to do this?
Yeah.
This in trig substitution, they're like, what if we just multiplied the entire thing by this?
You know, I think at its core, that's what it is. I don't think it's like random, like, hey, let's just throw a tangent in there and see what happens. I think it's thought out as like, hey, you know what, tangent is this and this, and it has this relationship, and maybe that would work, and then they work it out. And yeah, I mean, it's a process of someone proposing a solution to something, maybe getting shot down, coming up with a better one, and eventually saying, oh yeah, that actually does work. But yeah, that's kind of it. Like I said, this is like the stuff that, a PhD would do. I mean, the higher you get up in math, the more you realize that like math is still growing. There's still like stuff to be learned, and like the more you've learned, the more you realize the more you don't know. And so this, like I said, this is what a PhD would do. They'd be like, you know what? I would like to figure out what sound has to do with math in this regard, and then you would like spend the next like 3 years of your life trying to figure that out. You propose it, you present your work, and the PhD review board is like, no, that's terrible. You need to fix this, that, and the other thing. And then you fix it, and they're like, that's a little better. And then like a year later, you're like, I think it's good. And they're like, yo, that's awesome.
Where's PhD on like the scale of degrees, like with like doctors and stuff?
That's a doctor of philosophy. So in like the education or the counseling or other professional fields like that, it would be the equivalent of like a medical doctor kind of. I mean, obviously they do very different things, but it'd be like a terminal degree.
So like PhD,
Yeah. So we have a PhD. We have a PhD in our math department. Dr. Wenzel is a PhD. Dr. Rowe and Dr. Rowe, PhDs. Dr. who?
The Spanish teacher.
Yeah. And there's Dr. Wohlberg, English teacher. She's a PhD in English Lit or something like that. So,
Dr. Ren.
same thing. Same thing. Dr. Fisher, actual medical doctor, right?
Dr. Cord.
See, they're everywhere. All right.
Dr. Drake
Not real. Although good reference there. Okay, so you multiply everything through by the integrating factor. And then this is where I prefer not a formula, simply for the reasoning that I know myself well enough to know that when the pressure's on, I might forget the formula. And so I prefer to see a pattern. The pattern on the left eventually will hopefully become apparent that it's the result of a product rule. And so what we need to do is we need to like decompose the product rule and say, all right, fine, the left side is a product rule. And so in order for that to be a product rule, it would have to be ddx of something. What would the two factors have to be if that really is a product rule? Y was one of them, times e to the x squared. And you can always back check this real quick by doing 1d2 plus 2d1 with your proposal. So you could do 1 is y, d2 would be e to the x squared times 2x. That's actually the second term up there. And then ddx of y would be dy dx. Oh, look, 1d2 plus 2d1, the pattern fits. So, and this should always be the pattern. If you get the right integrating factor and you multiply it through there, that left side should end up being a product rule that you can pull back out of the product rule. Make sense? Okay. So then we're ready now almost to do our antiderivatives. I just need to multiply the dx over. So it's going to be d of y times e to the x squared equals 10x e to the x squared dx. Let's multiply that dx over. Now that I've separated those out, I'm ready to do my antiderivatives. So antiderivative of both sides. Left side, we just get y times e to the x squared. The right side, Timmy messed up a little bit, didn't he? I already got the 10 out of there. What do we need to multiply the inside by? Yep, times 2. So I will just use a different color for that. So make it a 2x, divide by 2. So now we get 5 e to the x squared plus c. And remember, when you're solving a diffie-q like this, the last step is always to explicitly solve for y. And so I'm going to divide everything through to get the y by itself. So my general solution would actually be y equals 5 plus c over e to the x squared. Liz.
So how did you get it to change from dy to dx?
So ddx, the way that I think about this, ddx is an action. It's like a verb. Like ddx means do the derivative with respect to x of whatever comes up next, right? And so what I'm saying here is that this whole left side could be re-expressed as the derivative with respect to x of something. So in other words, like, if I went off to the side...
Oh, okay, yeah, got it.
Are you sure? Because what I'm trying to say there is it's derivative with respect to x, that's what d dx means, of this product,
Yeah.
right? So it's not like I turned the dy dx into ddx. I just turned it into the ddx of a product versus the result of the product rule.
Yeah.
Josh?
In U, when we saw for U, why don't we have plus C?
Yeah, that's a good question. So like the plus c would be the constant of integration for your antiderivative, of course, right? What we're using that u equals e to the x squared for is simply an integrating factor to make the overall differential equation solvable. And so to put a plus c right there would be like, it's not like the c would not have anything to do with the solution to our differential equation. It's simply a tool to enable us to solve that differential equation. So really the only c we care about is the c that we'd get on the end there.
Because when we get that final, when we get that final C, it's only related with that other C.
You're not really, so you're not really like anti-differentiating anything. You're simply saying the derivative of what is x squared, right? And, or excuse me, the derivative of what is 2x? The answer is x squared. We're just trying to figure out what that would need to be to make this work versus like, so think of that antiderivative up there over the 2x. Think of it simply as like, we're just trying to like reverse engineer the integrating factor versus coming up with like an antiderivative.
Oh, I see.
Okay. Are you seeing the product rule now? Is that what you're...
I'm so confused when it came in.
It's pretty funky. Like you could always take what I proposed there and like ddx it and see that it's the same thing.
You guys playing some footsie?
I didn't come up with it. Somebody 200 years ago. So I'm seeing it as 1d2 plus 2d1 or 2d1 plus 1d2. So I'm looking at this and I'm saying, all right, is this 1d2 or is it 2d1? Is this 1d2 or is it 2d1? And I can see that in both there's an e to the x squared. So that to me is like, all right, I bet you one of the factors is e to the x squared.
So you just
and I see a y. So basically what I'm doing is like educated guess and check.
Yeah.
And then like real quick in my mind doing a 1d2 plus 2d1. I'm like, okay, it works.
Okay.
Or maybe it doesn't work and I need to make a small adjustment or whatever.
Gotcha.
Okay. Yep. All right, that's it, guys. Have a good weekend. See you Monday. So, hey, 7 on Monday, right? We're done with 6.
Oh, I thought you meant 7 a.m. on Monday.
No. Sorry, chapter 7.
Okay.
Right, I'll send you a reminder, but Liz, 5 on Monday, a.m.